Hi, I'm Professor Goins. In this video, I'm going to look at the volume of a solid of revolution, in particular the disk method, where we will consider rotation about the y-axis. So what I do is I take this area bounded by this graph x equals g of y, the horizontal lines y equal to c, y equal to d, and bounded by the y-axis. So this region right here, I take that, I spin it about the y-axis, and I create what's called a solid of revolution, given by this horrible picture right here. So then what we're going to do is we're going to figure out what is the volume formula for this. Well, remember that the volume is sort of conceptually here, and that's why I have it in quotes, the sum of all the disks. So what do we know about an arbitrary disk in this case, sort of in the deconstruction of this object? Well, we could think of a disk as one of these cross-sectional slices where the radius is given by the distance from the axis of rotation to the boundary here. Well, that distance is the same as the function value, so that's g of y. And the disks are stacked vertically, which means if they're stacked vertically, we're summing over all the y values from c to d. Said differently, we're integrating with respect to y. Okay, so therefore, here's my integration formula. For the volume, we're going to integrate from c to d, so that's just a fancy way to say a continuous sum from c to d. So I'm going to integrate from c to d of, remember, it's pi r squared, so it's the sum of the disks, and each one is pi r squared. So pi square of the radius, and the radius is g of y, dy. So let's look at a specific example. So let's say I take the graph y equals x squared, which kind of resembles that shape right there, and I'll initially give the interval over the x-axis between x goes from 1 to 2, but that graph bounded by these horizontal lines and the y-axis, I take this solid region right here, or this area, spin that about the y-axis, generate a solid of revolution, which is going to have a similar shape to this, and compute the corresponding volume. So here's the volume formula. It's given by the integral from c to d. So first of all, what's c and d? Well, if x is 1, what's the corresponding y value? Well, y equals 1 squared, so that'd be 1. 2, this point, what's the corresponding y value? Well, again, the point on the graph would be 2 comma 4, so this would be 4. And then it's pi times, well, look over here in our diagram, we've got this curve written in the form x equals g of y. Over here, I've got it written in terms of y equals x squared. So I have to take this equation right here and write it in an equivalent form where I have x solved for. So of course, in this case, all I have to do is take the square root. And yes, when you take a square root, you do have to account for the plus or minus. In this case here, this graph is in the first quadrant, so we would take the positive radical. So this would be the graph of x equals the square root of y. All right, so therefore the radius of this would be the square root of y, and then we're squaring that, and then dy. All right, square the square root, we get y, so this would be the integral from 1 to 4 of pi y dy. Antiderivative of pi y would be pi y squared over 2. Evaluate from 1 to 4. So I plug 4 in there, I'm going to get pi times 16 over 2. Minus, I plug 1 in there, I'm going to get pi times 1 over 2, which gives me a total of 15 pi over 2. So the one thing to keep in mind is that if I rotate this about the y-axis, and I was given an equation of the form y equals f of x, I have to convert it so that I have the form x equals g of y, and then this right here would be a radius. And you also have to keep in mind that if you were given the x values, or the values on the x-axis, I have to convert those to values on the y-axis And I can simply do that by taking these values and plugging them into this function, the y equals f of x, to compute the 1 and the 4 in this particular case to give me my y limits of interest.